Researchers from the Chinese University of Hong Kong are developing a new blood test that can detect cancer earlier, cheaper, and more accurately. Based on an approach called fragmentomics, it allows doctors to detect cancer by analyzing the size of DNA fragments in the blood. It can also help determine whether a painful biopsy is even needed. Professor Alan Chan is here to tell us more. Thank you for joining us, Professor Chan.
Thank you for inviting me.
An exciting new development in cancer screening indeed. Can you tell us, how does this new blood test work?
Okay, so let me start with the existing blood test for cancers. So in the existing blood test, it tests for proteins released by the cancer cells. But these proteins are released by the cancer cells for no reasons. It's just the cancer cells go wrong, and then in the mechanism, it releases some unrelated proteins. So in the present generation of tumor markers based on proteins, it is neither sensitive nor specific. Neither sensitive, it means that a lot of the cancers do not secrete this type of proteins, so that there are a lot of false negative test results. And false positive means that other conditions unrelated to cancer can also release these proteins into the bloodstream, leading to false positive results. So this is the generations of tumor markers that we are using in the hospitals. And then around a decade ago, we developed another type of tumor marker, which is dependent on the DNA testing. Because the core pathology of cancers is that the DNA is misarranged, and there are a lot of functional deficits in the control system of the cancer cells, so that its growth is not controlled like under the normal mechanisms. Mm-hmm. So what exactly control the function of the cancer cells is that in all the cells in our body, normally it carries the same sequence. So the brain cells and the heart cells carry the same sequence, but they carry out different functions. What control this is these different cells are switch on different genes, and the switch on and switch off of genes are dependent on a mechanism called methylation. So if a gene is methylated, then in general it is switched off, and if it is unmethylated, it is switched on. And because a lot of genes are misorganized and the control mechanisms are not functioning well
during cancer.
During cancers, mm-hmm. So a lot of aberrant methylations can be found in the cancer cells.
This is what it tries to detect then?
Yes.
This is what it tries to. So is this fragmentomics then? Can you explain more about this?
So for the detection of methylation, it needs a laboratory analysis. So it is best to be carried out in a central laboratory. So the procedure is a little bit complicated compared with other analysis of the DNA by just sequencing. So what it results in is the cost of that analysis is pretty high. So
this is what's currently available, like in the U.S. market.
Yes,
correct?
In the U.S. So in the U.S. market, it is now marketed as a test called Gallery. So it is sold at $950. So it is
not cheap.
It is very, very expensive, mm-hmm. And because the application of this is to screen for cancer. So imagine if we need to carry out a cancer screening test every year of almost $1,000 is probably not practical in the Asia market, and not even in Hong Kong, except only limited to a few very rich people. So what we think is we can develop a new generation which eliminates the necessity of directly measuring the methylation. So over the last few years, what we found is that the DNA in the cell, when it is released into blood, it is chopped into smaller pieces. Mm-hmm. And what governs the cutting pattern is the methylation. So a piece of DNA, if it is methylated and unmethylated, it will be chopped into different patterns. So based on how it is fragmented, we can deduce the original methylation status of the DNA, so as to determine whether a cell is a cancer cell or is normal cell.
Mm-hmm. So So this is fragmentomics then. It detects how long the DNA has been.
Actually, it sequences the DNA and look at the ends of the DNA. And then based on the exact fragmentation site of the DNA, we can deduce the methylation. For example, if a piece of DNA is methylated, then it would be cut exactly at the cytosine, the C elements of the DNA. But if it is unmethylated, it would be cut only one base, one nucleotide before the cytosine. So based on where exactly it is cut, then we can deduce whether a piece of DNA is methylated or
So
not.
this type of screening is actually more accurate than the current generation of blood
It's
screening?
similar in accuracy, but the good thing is much cheaper. We estimate that it's probably 1/5 of the cost. Because it uses a technology, is simple sequencing of the DNA. So for sequencing, it is extensively used in the clinics because probably 2 decades ago, we invented a method called non-invasive prenatal testing. Is a pregnant woman wants to know whether the baby is normal.
Has Down syndrome
Down
or
syndrome.
not, yeah.
Then we use sequencing of the plasma DNA to determine whether the baby has one additional copy of chromosome 21. So in the latest generation, we use exactly the same wet lab protocol so that it can be adopted by any laboratory for providing these non-invasive prenatal tests.
So then how does this test then transform cancer diagnosis then, would you say?
So
In terms of, early detection is key. How do you think this will then transform?
Okay, so in one proof of principle study, we screened 20,000 men in Hong Kong for nasopharyngeal cancer. So after screening, we identified 34 cases of nasopharyngeal cancer because early nasopharyngeal cancer is typically asymptomatic. So in Hong Kong, 80% of the patients presented with stage 3 and stage 4 disease normally without screening. But in our study, after screening, we identified 34 cases, and 70% of them had stage 1 and stage 2 disease. So because of the very significant shifting of the stage, then we show that for those individuals identified by screening, their survival improved by 10 times. So the mortality is reduced by 90%.
Wow.
So it means that if we can screen for early cancers using blood tests, we can reduce the mortality and improve the treatment outcome of these cancer patients.
So how soon do you think will this be widely available in the Hong Kong market?
So for the US test, it is already in the market, is being used clinically. But for the third generation, we are still in the research and development. So we are carrying out large-scale clinical trials to demonstrate that the long-term stability of the test, and also to when the accuracy is maintained in the large-scale study, then we would go through regulatory approval, because the regulatory approval may take more time than the development of the test.
So how long are we looking at then?
I think in probably 3 years' time.
3 years' time, okay. Well, we'll look out for that. Thank you so much,
Thank
Professor
you.
Chen. And to read more about the latest Hong Kong innovation, please visit scmp.com.